We have been asked to investigate and conduct a feasible study on whether speed bumps can be used to generate enough electricity to power street and road lighting. Before we began tackling the problem, we first had to find a few facts about the street lights and about speed bumps and make a few assumptions. An average street lamp is on for 8 hours a day and requires 80 watts of power. An average speed bump is roughly 0.1 meters high. If we were to use springs, we would assume that they are stiff enough to support the weight of the vehicle, and that we took acceleration due to gravity as a constant of 9.81 meters per second squared.
As a group, we came up with a few initial ideas as to how we can obtain energy using a speed bump. Our first idea was a rolling speed bump, so that when a car rolls over it, it will turn a motor generating electricity, kind of like a treadmill. Our second idea was solar panels, so we can obtain energy using the sun, but we decided to go with a pressure pad system on the speed bump.
We decided to focus on using pressure pads to oscillate a spring within a magnetic field. As the car goes over the speed bump is compressed, which causes the spring to oscillate. This then cuts magnetic flux between two magnets which we have placed on either side of the spring. This causes an EMF to be induced, which therefore induces a current in the wire which is attached to the spring. This means a charge is present which can be stored in a capacitor and then used to power the street lamps later on.
To calculate the energy stored in the spring, we use E equals a half kx squared, where F equals kx, and therefore K equals F over x. This gives us E equals a half Fx, with F in terms of mg. We then assumed the average mass of a car to be approximately 1,500 kilograms. We would take the compression of the spring to be equal to the height of the speed bump, which we have assumed to be 0.1 meters. Using these figures, we calculated the energy output when one car goes over a speed bump to be 736 joules each time. This means that each time a car passes over a speed bump, it will provide enough energy to power a street lamp for 9.2 seconds.
If we assume that every streetlight has one associated speed bump, in order to keep the streetlight on for 8 hours, approximately 2.2 cars per minute must go over the speed bump. To test that this was feasible, we counted 121 cars going down a road in 30 minutes. This is roughly 4 cars a minute, which means that it will create enough energy to be feasible.
Our system requires 2,304,000 joules of energy per streetlight to operate. Using our figure of 4 cars per minute, the average output energy is 4,239,000 joules. This means our system can have an overall efficiency of 54% and still operate.
Some of the key advantages are, this is a source of renewable energy. It will save money in the long run, which could be used to improve the local area, and it will be safe during a power cut.
However, there are also some disadvantages, namely the cost of installation and maintenance fees. It could be a hazard to cyclists and the potential danger to all vehicles during bad weather. To conclude, we decided that although it's possible that the system can be maintained on an average day, that doesn't necessarily mean that it's guaranteed to be functioning correctly every day all year round, and the safety implications of not having streetlights working on busy roads outweigh the benefits of a potentially working system.